Okay, hello there, good people. Today we are talking about the laws of thermodynamics. Today we do have a slideshow, which I know is incredibly exciting for you, and I can't wait to share with you all of the content from the slideshow. So we're going to be talking about the laws of thermodynamics. There are several, and if you had to start with one, if you had to choose a place to start with the laws of thermodynamics, you would probably choose to start at the, zeroth law of thermodynamics. The zeroth law of thermodynamics says if system A is in thermal equilibrium with system B, and system B is in thermal equilibrium with system C, then system A is in thermal equilibrium with system C. Hey, does this sound at all like math to you? Because here's what I'm thinking it sounds like. It sounds like if A is equal to B, and B is equal to C, then, well, eraser? Boop, 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 boop. Sorry, that's embarrassing. Then A must also equal C. You've seen this play out in reality before. It's not just a nice theoretical concept. You've actually seen it play out in reality in the lab. You'll remember from the lab that I had a beaker full of boiling water, and then I had little metals in the bottom of the beaker. And when you came up to get a metal, you said, Miss Wilson, can I please have that metal? And I said, yes, but of course. And then I told you the temperature of the metal. But I wasn't really reading you the temperature of the metal. I was reading you the temperature on the thermometer. And the temperature on the thermometer told you the temperature of the water. But here's the idea. If the thermometer is in thermal equilibrium with the water, and the water is in thermal equilibrium with the metals in the water, then the temperature on the thermometer is the same as the temperature of the metal because the thermometer and the metal are in equilibrium with each other. If A is in thermal equilibrium with B and B is in thermal equilibrium with C, then A is in thermal equilibrium with C. That's the general idea. If the temperature of one thing is equal to the temperature of another thing and the temperature of the third thing is equal to the temperature of the second thing, then the first thing has the same temperature as the third thing. That's the idea. That's the zeroth law. Let's talk next. Maybe. I need a mouse. Let's talk next about the first law. The first law of thermodynamics is really just a version of the law of conservation of energy. And here's what it says. It says that delta U is equal to W plus Q, where delta U is the change in internal energy of the system. Please add this equation here to your bag of tricks. Okay, please add this equation to your bag of tricks. Now, in the past, we have said that U is potential energy, but today U will be internal energy. We've talked about internal energy in the past. Internal energy is all of the energy that comes from what the molecules inside of a substance are doing. So it's all the internal energy from those, all the energy from the bonds in the molecules, all the energy from their thermal speed, and all of their mass energy. I said thermal speed, you know what I mean, all their kinetic energy. Here we're talking about a change in internal energy. We say that if you want to change the internal energy of a substance, you can do one of two things. You can either add work or add heat. Let's look at what this means. I'm going to make this a little bit bigger here. Oh gosh, let's not do that. Let's not do that. Let's get a cursor. Okay, here we go. Make this a little bit bigger. Okay, perfect. Oh gosh, wow, you can see I'm creating all kinds of issues here. Okay, here we go. Here I have a little gas in a little container. Now, one thing that I could do if I wanted to increase the energy of the little molecules inside of this little gas is I could take a flame, a blowtorch, and I could heat it up like this. And if I heat it up, well, then they would have a little bit more thermal energy. They'd be moving quite a bit faster. And so we'd say I just increased the internal energy of the system. So that's one thing that I could do. Here's another thing that I could do. Another thing that I could do is I could take my hand up here on the top like this and squish it down like this. And I just added energy into the system. There are a few ways to think about it. One way to think about it is that I just did work. I applied a force like this and I went this direction. So when I go like this, I apply work. Work is the transfer of energy. So I just transferred energy into this thing. That's one way to think about it. Here's another way to think about it. When I push down, don't I shove on the little particles that are in there? If any of those little guys who were in there were not moving before, when I shove down, I say, hey, you better get moving. And I make them all start running downwards. Well, didn't I just add in internal energy because I made the little molecules start moving quite a bit faster? So I can add energy into this system here. By this system, we mean this little gas. Whoa, I did not mean to change the slide like the way that I did. I can add energy into the system. I could add energy into this gas by either adding heat in or by doing work on the system. Now, let's talk a little bit about sign conventions here, because our sign conventions are going to be opposite of the sign conventions that your textbook uses, and I will explain why we use those opposite sign conventions. Let me get this erased here really quick. Okay, here we go. I need a cursor. Okay, here are sign conventions. We say, and this is opposite of what your textbook says, but we say that work is positive if work is done on the system, and work is negative if work is done by the system. Here's why we say it that way, is because I like to talk in terms of what the gas is feeling. If I do work on the system, notice I apply a force and I go a distance to the gas. That's something that is happening to the gas. When I do work on the gas, well then I just increase the internal energy. So the gas says I now have more energy than I did before. But check this out. If I squish it down, sorry, I can make this big again. If I squish it down like this, and then I let it go, notice the gas pushes up on the plunger. The gas just did work on the plunger because the gas pushed the plunger with a force for a certain distance. And so if the gas pushed the plunger, it did work on the plunger. Now that means that this gas just lost a little bit of energy and it gave its energy to the plunger. Notice the plunger had no kinetic energy, then some kinetic energy. And so because the gas gave its energy to the plunger, the gas now has less energy, so it lost energy. Your textbook does the opposite. Instead of talking about what the gas feels, it talks about what the environment feels. So it would say, well, the gas just added energy to the environment, and here the environment just lost energy as it gave that energy to the gas. But we like to talk in our class, we will always talk about what work does, or what energy happens to the gas or happens to the system. So we say that work is positive if work is done on the system. Energy is given to the system, and work is negative if work is done by the system, if the system gives some of its energy away. We also say that heat is positive if it's added to the system. We call that an endothermic process. I can't shrink this down anymore. Okay, wait, oh gosh, oh my GOSH. Back. Okay, sorry, I'm just having all kinds of crises here. Why am I still in the do you see I'm still in the shrinky mode? Okay, yes, perfect. Oh gosh, guys, I'm so sorry. I do apologize. Go up here. Okay, we say that work is positive if it's added to the system. We say that that's endothermic. We say that work is negative if it's removed from the system. That's exothermic. Isn't that what we've always said? If you add heat to something, we say positive heat because that's the amount of heat gained by that thing. And if we take heat away from something, we say that that's negative heat. That's the amount of heat that's lost by that thing. So endothermic processes, we say you have heat added, that's positive. And then for exothermic processes, we say that you have heat lost, that's negative. So those are our sign conventions. That is the first law of thermodynamics. We will be applying the first law of thermodynamics a whole lot tomorrow. Today, we're kind of just, here's a little intro, but in our next video, you'll see that we apply it a whole lot more. Okay, oh, and look, all the letters are there. Okay, next. The next law of thermodynamics that we're going to talk about today is the second law of thermodynamics, which is often called the law of entropy. Now, the law of entropy has a whole lot of stuff to it, so I'm going to kind of make 4 points. When I make these 4 points, I'm just going to kind of talk through them. I'll say this is the first point, this is the second point, this is the third point, and this is the fourth point, and I'll talk through each of these 4 points. When I talk through each of these 4 points, they are all kind of encompassed by the law of entropy, so all of them are worth writing down. I'm going to make this big, though, because I'm just really going to talk at you for a second, and that's all that's about to happen. Okay, let's see. Let's make this bigger or not. Guys, in case you haven't noticed, I'm struggling today. Come on, buddy. You can do it. I believe in you. Doesn't care about my belief. It says, whatever, Miss Wilson. Oh, gosh, no spoilers. Okay, well, never mind. I give up. I give up. No spoilers. Okay, well, I could make this very big, but I fear I won't be able to go back. Let's try it. Whoa, okay. Here's the first idea of the law of the second law of thermodynamics, or the law of entropy. The first idea of the second law of thermodynamics is that randomness is more probable. That's the first idea of the second law of thermodynamics. Idea number 1. Randomness is more probable. Randomness is more probable. Here I have a Rubik's Cube. Now, if I were to close my eyes and I were to turn this thing back and forth a few times, is it possible that I could open my eyes and this Rubik's Cube could be totally and completely solved? Is it possible? Yes. Is it probable? No. Here's the idea. How many configurations are there of a Rubik's Cube that is a completely solved Rubik's Cube? Like, how many different ways does a solved Rubik's Cube look? How many different things would you look at and say, that Rubik's Cube right there, that's solved? Only one. There's only one way for a Rubik's Cube to be solved. But how many different ways are there to look at a Rubik's Cube and to say, that Rubik's Cube is not solved? A lot. There are a lot of ways for a Rubik's Cube to be unsolved. There's only one way for a Rubik's Cube to be solved. So if I close my eyes, the probability, and I shuffle this around, the probability of me landing on something that's unsolved is way higher than the probability of me landing on something that's solved, because there's only one way to be solved, and there are tons of ways to be unsolved. We say that randomness is more probable, because there are more ways to be random than there are to be organized. Here's another example. Suppose that I took a box of puzzle pieces, I shook it up real nice and good, and I took off the lid, and I laid all the puzzle pieces on my table. How many ways are there that a puzzle could look totally and completely solved? One way. There's one way that you could arrange all the pieces that we would say that puzzle is solved, and it looks like a beautiful picture of a Ferris wheel. There's one way to do that. But there are tons of ways for puzzle pieces to look unsolved. The odds of me taking a box and dumping it out on my table and it all coming out solved, well, that's only one possibility. But there are so many more possibilities. There are so many other ways that it could be unsolved. So randomness is more probable because there are way more ways. There are a gazillion ways for a puzzle to be unsolved. There's only one way for it to be solved. What are the odds that the wind blows across the Sahara Desert today, and then it blows all of the little grains of sand into a sand castle? Is it possible? Yes, it is possible. Is it probable? No, because there are only so many ways that sand can be arranged to make a sand castle, but there are way more ways that sand could be arranged to look like giant piles of sand. And so, most likely, when the wind blows across the Sahara, the sand will end up looking like giant piles of sand, because there are more ways to be random, like giant piles of sand, than there are to be organized, like a sand castle. This is the first part. This is statement number 1 of the second law of thermodynamics, or the law of entropy, that there are more ways to be random than there are to be organized, so randomness is more probable. We have a special word in physics to represent randomness or disorganization, and that word is entropy. We say that if you are in a state of high entropy, that means you have a lot of randomness. If you are in a state of low entropy, that means you have a lot of organization. So entropy is a word of talking about randomness. If I were to look at a puzzle, and that puzzle had high entropy, a high entropy puzzle would look like a bunch of random pieces all scattered on the table. A low entropy puzzle would look like a puzzle that's all fit together, making a picture of a Ferris wheel. This right now is a high entropy Rubik's Cube. If I wanted a low entropy Rubik's Cube, I'd probably have to take this Rubik's Cube to Mr. Duncan. He could solve this for me and make it look nice and low entropy, nice and organized. We'd have all the colors on one side here, all the colors on one side here, and then one color on this side here, and one color on this side here. This is the idea of the first idea of the second law of thermodynamics, is that high entropy is more probable, it's more probable than low entropy. More randomness is more probable than less randomness. And that's the first idea of the second law of thermodynamics. Here's a second idea of the second law of thermodynamics. Because high entropy is more probable, because randomness is more probable, it's easy to go forwards in randomness. It's hard to go backwards in randomness. Or another way of saying this, it's easy to increase entropy. It's hard to decrease entropy. You know this if you ever grew up with a younger sibling before, because you remember when you spent so many minutes meticulously stacking those little blocks to form a brilliant tower. And then your younger brother comes waddling in and he knocks the whole thing over as he just makes a mess the way that younger brothers do, as they kind of just pummel through everything in their way when they're little tiny toddlers just learning how to walk. And do you remember watching as your little brother knocks over your tower and you go, no? And then all of your little blocks are all in pieces, a little pile of rubble on the floor. It's much easier to wreck a tower than it is to build a tower. Why? Because higher entropy is easier than lower entropy, because it's more probable. There are more ways for your tower to be knocked over and in a pile of rubble, and then there's only one way to build the tower that you really want to build. And so because of that, it's way easier to increase your entropy. It's way harder to decrease your entropy. If you take a puzzle and you put all those puzzle pieces out on the table and you organize them all to form a puzzle, you solve the puzzle, it looks beautiful. Wow, your Ferris wheel is amazing. It took you hours to do that. It takes about 5 seconds to take all those pieces apart and put them back in the box. It's easy to increase entropy. It's harder to decrease entropy. You take an egg. An egg, if I was holding a little egg in front of you, you'd say, that's a very nice looking egg, a very low entropy kind of thing. And I would say, yes, of course it is very low entropy. It's very organized. It's not that random. You got a nice shell on the outside. Then on the inside, you got some egg whites. Then at the center, you got an egg yolk. 3 little parts organized very, very nicely, all split up into different parts. Now, if I were to take that egg and I were to accidentally drop it on the floor so that now the egg is smashed into tons of pieces, well, that is a much higher entropy state. Now little pieces of the egg yolk are kind of sliding into the egg whites, and the egg whites are mixing with the egg yolk, and the eggshell is kind of all in the middle of all of it. It's a very random kind of thing, a very chaotic, very kind of messy kind of thing as everything kind of blurs together. Increasing the entropy of an egg, cracking an egg, is easy. Decreasing the entropy of an egg, uncracking an egg, is hard. All the king's horses and all the king's men can't do it. To take an egg and to take its entropy backwards, that's very, very hard. Because of this, the entropy of the universe is always increasing. Because it's easy to increase entropy, it's very, very hard to decrease entropy. We'll talk about this more in a second. But another implication of point 2. Point 2 says that it's easy to go forwards in entropy. It's very hard to go backwards in entropy. Or in other words, it's easy to increase entropy. It's very hard to decrease entropy. One of the implications of this is that the universe, or the entropy of the universe, is always increasing. Because it's easy to go forwards in entropy. It's hard to go backwards in entropy. Okay, let's talk about point number 3. Point number 3 is that thermal energy is the most entropic form of energy, or thermal energy is the most random type of energy. Thermal energy is the most entropic type of energy, or it's the most random type of energy. Here's what we mean by that. Gravitational potential energy, that is very organized. You got a planet right here. I got a little mass right here. I lift that little mass up. I got mass up here. I got planet down here. Wow, look, everything is nice and very organized. Chemical bonds, energy stored in chemical bonds, that is a very high, that's a very low entropy kind of format, very organized, not that random of a type of energy. You got little bonds, and the little bonds have a little bit of energy, and look, you have a little molecule here, and a little molecule here, and look, you little break your little bond, and then you get a little energy, that kind of thing. That's a very organized form of energy, stored in, chemical potential energy stored in bonds. Thermal energy. Wow, sorry, did you see how long I hesitated there? I totally lost track of what I was saying. Thermal energy is a very random, a very chaotic form of energy. It's just energy from things moving around randomly crazy fast. That's all that it is. It's just stuff moving fast at random angles at random speeds. That's what thermal energy is. It's just from what we call Brownian motion, which is the random chaotic motion of particles. Even in the definition of Brownian motion, you see that it has a lot of randomness to it. Thermal energy is the most entropic form of energy. Thermal energy is the most entropic form of energy. That means that point number 4, because thermal energy is the most entropic form of energy, and it's easy to increase entropy and it's hard to decrease entropy, that means that all energy is eventually going to become thermal energy. All energy is becoming thermal energy. Let's say that you take a chair and you put that chair up on a table. Well, you did increase the gravitational potential energy. That is absolutely true. But also you're feeling a little bit warmer now after lifting that chair than you did before. Why? Because some of your energy that was stored as chemical potential energy in the bonds of your food, some of that energy went to gravitational potential energy, but some of it also went to thermal energy. Thermal energy is the most entropic form of energy, and so all energy will eventually become thermal energy. Oh, there's the bell. Because it's the most entropic form. Now, all of this leads to all of these 4 ideas lead to kind of a summary statement for the second law of thermodynamics. If I had to summarize the second law of thermodynamics, I would summarize it in this one statement, which is that the entropy of the universe is always increasing toward a maximum value. Oh, wow. Okay, this is all, I think, going to work. Hopefully. Yes, the entropy of the universe is continually increasing toward a maximum value. It always has been increasing, and it always will be increasing. High entropy or randomness is more probable than low entropy, and so because of that, it's easier to increase entropy. It's harder to decrease entropy, and so because of that, we are always increasing the entropy of the universe. Now, some of you say, are we really always increasing the entropy of the? Oh gosh, some of you are saying, are we always really increasing the entropy of the universe? Yes, we are. Even when your mom says to you, hey, we're having guests over, it's time to go decrease the entropy of your room, and you say, okay, Mom, and you go upstairs to decrease the entropy of your room because, let's be honest, your room is starting to get a little bit of a high entropic kind of state. You got your clean clothes on the floor, you got dirty clothes on the floor, you got all kinds of stuff on the floor. So you say, okay, I'm going to go decrease the entropy of my room, and you walk upstairs to your room. Now, first you look around and you say, wow, we got a lot of work to do. You pick up a shirt, you fold that shirt, and you put it in the drawer with the rest of the shirts. Bam, decrease the entropy. It's a little bit more organized now because the shirts are with the shirts. You pick up the dirty socks off your floor, and you take those dirty socks and you put them in the dirty hamper with the rest of the dirty clothes. Bam, a little bit more organization. Now the dirty clothes are with the dirty clothes. Then, after that, you take your sweatshirt, that hoodie that's been sitting on the floor. It's been clean this whole time. You just haven't worn it or put it away. It's just been sitting there on the floor. You take that hoodie, you take a hanger, you put that hoodie onto the hanger, then you take the hanger, you put it up in the closet. Bam! You just decrease the entropy of your room. Now the hoodie is with the rest of the hoodies. More organization. Then you make your bed, which you don't remember the last time that you did, but it's made now. And at the end, you lay back down on your bed and you survey your work and you say, wow, I really did just decrease the entropy of my room. That was pretty impressive of me. Whew. I'm hungry. I could use a snack after all that work. Why? Because decreasing the entropy of your room took energy. Some of that energy went into things like increasing the gravitational potential energy of your hoodie as you hung it up on a hanger. But some of that energy, in fact, a lot of that energy went to heat. You're feeling a little bit warmer now than you did before you started cleaning your room. So in other words, a lot of the energy that you put in became thermal energy. So here's what happened. You might have decreased the entropy of your room, but in order to decrease the entropy of your room, you had to turn a lot of energy into thermal energy, which increased the total entropy of the universe. So even though you decrease the entropy of your room, you increase the entropy of energy because you turned a lot of energy into thermal energy. And so for the net universe, the whole universe actually just ended up increasing in entropy. Because even though you decrease the entropy of your room, it cost you thermal energy, which has a higher entropy. This means the entropy of the universe is continually increasing toward a maximum value. This this is the second law of thermodynamics, which we saw in 4 statements. And now we are going to see some implications. There are 2 implications that we're going to look at today for the second law of thermodynamics, or the law of entropy. The first is the heat death of the universe. The heat death of the universe sounds dramatic, because it is. Here is the idea of the heat death of the universe. The heat death of the universe says that the entropy of the universe is going to keep on increasing until it reaches a maximum value, until everything is as random as it could possibly be. Here's what will happen at that point. Imagine that I took an egg, and I dropped the egg, and the egg landed on the ground, and now I have egg yolk and egg whites and shell, and they're all kind of mixed together a little bit. They used to be all nice and separate in our very low entropic, very organized egg, but now we have a very random, chaotic kind of egg sort of mess on the ground. Well, let's say that I took that egg, and I put it in a mixing bowl, and I started to mix, and I mix. As I'm mixing, I'm increasing the entropy. And as I mix, I keep mixing it all together until I can't tell the difference between egg yolk and egg white and shell anymore, because they're all mixed together. They're not separated out at all. That is the fate of the universe. The idea is that all matter would mix together until you can't tell the difference between one thing and the next, because it's all mixed, so it all kind of looks the same. At that point, all energy will become thermal energy, because thermal energy is the most entropic form of energy. The same way that all eggs are on their way to being cracked eggs, all energy is on its way to being thermal energy. In the same way that you can't uncrack an egg, really, and we can't have eggs that are that are cracked that go backwards, eventually all of the energy in the universe is going to become thermal energy with no going back. At that point, when all of the energy in the universe is thermal energy, we know that heat always flows from regions of high temperature to regions of low temperature. What will happen is all of the regions of high temperature, all the heat will flow from regions of high temperature to regions of low temperature until everything is in thermal equilibrium with everything else. And at that point, everything will be at the same temperature. So all matter will look the same as all other matter. Everything will be at the same temperature. Now at that point, you won't have anything that ever happens anymore, because there will be no energy that's flowing from one thing to another. No energy will be moving around, and everything will look the same. So you won't have any events anymore. Nothing will ever happen. And if nothing ever happens, if there are no more events anymore, then there's no such thing as time, because time is the measure between one event and the next. And if you don't have events, then you don't have time. There's no way to talk about the difference between this moment and the next, because there are no moments. And so that is what we call the heat death of the universe. It's when everything looks the same, everything is at the same temperature, there are no more events and there's no more time. And that's the fate that we are marching towards. But we still have a long time until we get there. The next implication is what we call the arrow of time. Here's the idea of the arrow of time. The idea of the arrow of time is that time always points forward like an arrow. Now, we're not really going to talk about time travel today. We will talk about time travel way more in Unit 13. But for today, all that you need to know is that time can only travel forwards in one direction, at least for things with mass. Time always marches forwards. If we were to go back in time right now, then somewhere in the universe, an egg would have to uncrack. And that uncracking would have to happen without any energy getting turned into thermal energy. And we know it's impossible to uncrack an egg without using a little bit of energy to do it, or a lot of bit of energy to do it, to put all the pieces back together again. Whew, that would take a lot of energy. It'd take a lot of energy to do it, and a lot of that energy would become heat energy. So if you need to go back in time, you would have to unfry eggs and also uncrack eggs and also unfry pancakes, and your whole breakfast would have to get undone. Bacon would have to uncook. And so because we can't go backwards, unscrambling eggs, unfrying eggs, bringing those eggs back into their shells, because we can't do that without adding extra entropy in the form of heat in the form of thermal energy, then there's no way to go backwards in time because that would require decreasing the entropy of the universe, going back to a state where the entropy of the universe was lower than it is now. So those are our two implications of the second law of thermodynamics. Now, the third law. Third law is nice and quick and easy. It says that absolute zero cannot be obtained in a finite series of steps. You know Zeno's paradox, yes? And if you don't know Zeno's paradox, you do know Zeno's paradox. You just don't know that you know Zeno's paradox. Hey, if I started over here, that's smiling, by the way. You can't tell. If I start over here and I said I wanted to end up over here, and I was going to travel. Oh, no, I wish I had an undo button. I don't have an undo button on here. Okay, suppose that I was going to travel across the room. And that when I travel across the room, I am going to do it by going halfway every single time. So first, I go halfway across the room and I end up right here. And then I go halfway of the remainder of the distance and I end up about right here. And then I go halfway of the remainder of the distance and I end up right here. And then I go halfway of the remainder of the distance and I end up right here. And then I go halfway of the remainder of the distance and I end up right here. And then I go halfway of the remainder. Hey, how long is it going to take for me to cross the room? Infinity time! I will have to keep on walking for the rest of my life and then on into eternity. There is no way to cross the room by going by halves to actually make it across the room in a finite series of steps. That's what the third law is like. It says absolute zero cannot be obtained in a finite series of steps. Here's why. If you have something that is very, very cold, and you need to make that cold thing even colder, well, that's hard to do, to take out that energy. But then if I do it, if I take that cold thing and I make it even colder, and now I need to make that colder thing even colder, well, that's even harder than it was to do to make the cold thing colder. Because now it's a colder thing that I have to make colder. And so that's even harder to do. It's harder to get out that little bit of energy. But let's say that I take out a little bit of energy. Now I have something that's even colder. And I need to make that colder thing even colder. Well, now it's going to be even harder to make that even colder thing even colder. Because to make that colder thing even colder, I have to take out a little bit more energy, and it's going to be harder to do than it was before. Each little bit of energy that you have to take out is harder than it was to take out before. And so by the time I get to the last little bit of energy, how hard is it to take out the last little bit of energy? Infinity hard. It's infinitely hard. Each little piece of energy is harder to take out than the little piece of energy before it. And so to take out the last little piece of energy is going to be infinitely hard. And so we will never make it to absolute zero because we can never suck out that last little piece of energy in a finite series of steps. The same way that you can never cross the room in a finite series of steps. We've gotten close to absolute zero, but we can't ever make it all the way there. And that is the third law of thermodynamics. That gives us, 3 laws of thermodynamics, but really 4 because we started at 0. Oh gosh. Clear. The 4 laws of thermodynamics, you'll remember, we'll do a quick refresher and then we'll get out of here. Oh, I forgot. I'm still in the marker mode. Let's go back to cursor mode. Okay. The 4 laws of thermodynamics. First, we started with the 0th law, which says that if something is in thermal equilibrium with another thing, and then that thing is in thermal equilibrium with another thing, then the first thing is in thermal equilibrium with the third thing. Basic math. Then we said that the first law says it has to do with internal energy. We say you can increase the internal energy of a system by either adding work or by adding heat. Then we talked about the second law of thermodynamics, which is the one where we spent most of our time talking about how randomness is more probable. Because randomness is more probable, we're always increasing entropy. Thermal energy is the most entropic form of energy, and because of that, all energy is eventually going to become thermal energy. We talked about the implications being the heat death of the universe and the arrow of time, and finally we ended by talking about absolute zero and how it cannot be obtained in a finite series of steps. You're never going to be able to get those molecules totally and completely still because it always takes just a little bit more energy to get them to be just a little bit more still. And that's all for today, folks. I do hope that you have a wonderful rest of your day, and I'll see you all next time. Bye, good people.